So what I will try to do today is I will try to guide you through how does a sensor, optic sensor, fit in a system. And I will use an example that I've worked on myself, a metal printer system. So it's a company in the same market as ASML, but this is the very non-critical layers, the upper layers with the copper lines on it. And the idea is that I want to guide you through the question, if I make a sensor, I'm using some optics technology, where does that sensor fit in? And in this example, the sensor is part of a camera, and the camera is used in an optics chain, and this optics chain is used in an alignment subsystem, and the alignment subsystem is part of the printer. And the printer is used to print a pattern from a master wafer on another wafer. So I'm guiding you through this whole system, but while I'm doing that, I'm going to challenge you to think about the technology that you are working on yourself, and challenge you, how do you use that technology, where is it used, and try to understand how your technology fits in the broader system. So let me start with the printer system itself. So that is the system in the end that we would like to build. And this system is a system where you put in an entire wafer with the desired pattern, and you put in an empty wafer, and the system through an electrochemical process prints the metal pattern on the wafer, on the empty wafer. And that is then 3 process steps to do it, while in the current fabs it takes 8 steps to do this. So it's a significant simpler and faster process than the current process in the fabs. On the left hand side you see examples of the copper patterns that you can print on these chips. So I start with a question to you. In this presentation, I'm using this printer system as example. You see at the right hand side, you see the different levels that I distinguish. I showed them also on the first picture. And my question to you is, where are you yourself located? So are you a technology provider? Do you develop a sensor? Do you develop a device? Do you develop a component, a subsystem, a system, or the application? So where are you in this chain? And in your domain, and for the system or component that you're working on, what are these various levels? So try to locate yourself on this axis.
But it should be done then in the Google Docs.
Yeah, so let me show the Google Doc here. Oh, this is not the Google Doc, this is the real spreadsheet. I must have this one. Here's the Google Doc. So what you see here in
We
column.
can't see it on the screen, by the way. Now.
Yeah, you should see it on the screen now.
No, we see the presentation. Yeah, we see not yet. Now we see it on the screen.
Yeah. So there is some delay.
Okay.
Yeah. So what you see is in column C, it states in row 2 imaging sensor, and you can fill in your own on your own line what technology is it that you use. And then there is column E, and it says device, and I'm using the camera, but you can use the device that you think you are making. And then you go to the right, you get the imaging chain, alignment subsystem, and then just outside now is the system, which is the printer in this case. So you may already fill these in the columns in the spreadsheet. The technology, the device, the component, the subsystem, and the system. And if you have questions, you can use the chat So I have, as you can see, the chat window open so they can see if anyone has a comment or question.
And also we have unmuted everybody, so they can also ask a question live. Not everybody has unmuted him or himself, but
yeah,
questions
live questions are welcome too. Yeah, absolutely. So use the chat or speak up if there's anything unclear. So please try to fill in your columns. Now I see something happening. Another thing I learned is I now and then have to make a backup because in one of the sessions someone deleted by accident part of the spreadsheet.
Okay. Now you can undo any action. So
yeah, that's an option. That I'm not sure how far you can get there.
Ik kan nog steeds niet in een cellentype zo te zien.
you might have to refresh. Just hit F5.
Okay, let's try. Nee. Ja, dat helpt.
Yes, good.
maybe Gerrit, you can, because some people just entered or have been admitted. Maybe you can tell the newcomers just a short introduction.
Yeah.
To him.
Yeah. So people who just came in, I asked people to describe where they are working on. So are you working on a technology or on device? Then write in the column technology what technology you're working on, and then what device will be using that technology, and then what component will be using that device, and so on. And if you're working on a subsystem, then you go in the other direction and you say, I'm working on an alignment system and I'm using this component, and then in the end you end up with some photonics technology.
Interesting to see what everybody is filling in.
Yes, so I'll go a little bit down and I can see. Fader wears a lot already. Dimitris also, yes. You're already ahead, yes. So I will come back to the KPP. So, but it's of course okay if you work ahead. So we'll go step by step through the examples and then see what are the key performance parameters at that level. But we have the whole session to do that. And I saw, Dimitri, that you wrote various, a fader it was, various on the component and subsystems. Try to pick one interesting example of a component and a subsystem that's using it. Because then you will see what these higher levels of systems, what they expect from your technology. So, of course, technology can be used for many systems and devices, but pick one that is interesting to explore. Yes, I think that we are progressing well. So I will gradually go back to the presentation and talk a little bit more through the example. So I'm switching back to the presentation. Here's the presentation. And now let's have a look. So what you see in the spreadsheet is these different levels. And now I'm taking the step from a printer system to the alignment subsystem. And if you take two wafers and you want to print the pattern from one wafer on the other wafer, you have to make sure that you print it at the right spot. And that function is called alignment. And in order to align on the wafer, there are markers. You can see that on the top of the image. And in order to align, the system inserts a microscope between the two masters, between the two wafers. So you can look up and you can look down. And then they use a camera to get an image of the markers. And when you have the markers, then the camera acquires an image. The software searches for a marker, determines the center of the marker, and then tries to get the top and the bottom marker on top of each other. So it looks for the replacement, and then it moves the stage in order to get the master and the wafer well aligned. So that is the alignment process, and that is the purpose of the microscope and the camera. And now I jump to the bottom of the stack. So I say, well, let's look at the imaging sensor that is in the camera. So that's the technology that we are using. So there is some sensor, and that sensor may have some whole set of pixel sensors with vertical and horizontal controls and A to D converters. And out of this array comes a raw digital image. And then you can think about, so what are now the key performance parameters of this imaging sensor? And what I'm asking you is, what do you think are the key performance parameters of the technology that you are using? So to give the example, I did this for the sensor and for the imaging sensor. Key performance parameter are things like the spatial resolution and the contrast resolution, the frame rate, how fast can I image, the time to acquire one image, the uniformity of an image, the size of the sensor, the energy consumption. All of these are important parameters of that sensor. So challenge for you is now take your own technology and make a similar list. And in principle, this list, when you make it, the next step is that you would fill in numbers, and the numbers are the things that you agree with the supplier and the user of this technology agree on the numbers, and they have a contract on that. So typically, key performance parameters are smart, specific, and measurable. For now, I'm only looking at for what are these parameters. So if we go to the spreadsheet, then in the column D, fill in what do you think are the key performance parameters for the technology that you're using. Morgen.
Hoe gaat het, Geert?
Goed. Ik zit tot 11 uur in een vergadering.
11 uur, oh.
Ja.
Jou nog voorgelezen? Ja, ziet.
So try to fill in the, here, Carol did fill in the number.
Yes.
Hugo, yes.
Yeah, I'm still adding, trying to add. Just a moment.
Yes. So typically you have 5 to 10 of these key performance parameters. And I mentioned this word smart, specific and measurable. Those are the essential challenges. So if you say accurate solver, so how do you express the accuracy? The accuracy of what? Try to make it as explicit as possible.
Hier, kijk, dit is het volle blaadje.
Yes, I have the impression that we are getting to a saturation level. So let's move back to the presentation. So now I'm moving from the sensor to the camera. So I move one step out and look at what is the sensor, where is the sensor being used. So the first thing that we can do is we can look at how does the camera look like. And then you see that there is a block diagram, and the top left hand, there's the image sensor, and then the camera has all kinds of electronics in it. There's firmware in it, it has a network interface, it has a power interface, there's air and heat coming in, and there's packaging around it. So you see this is really now a device. And now you can ask the same question again. What are now the key performance parameters of the camera, of the device, the camera device? And similarly, what are the key performance parameters of the device that is incorporating your technology? And again, here is my list of examples. So again, you see image quality, acquisition performance, but you also see a number of device-specific topics: camera size and weight, camera energy consumption, thermal stability, the camera cost price, storage capacity, how many images, compression is added, the sort of weight and the quality. So what you see is that from the technology to the device, other key performance parameters appear that we didn't see at the technology level. So please fill in these technologies in the spreadsheet. Oops, wrong. So.
Come, finish.
Yeah. I think we generally get the information in. Hugo Cornelissen, can you say something about what you have answered? Can you tell a little bit about the technology and a little bit about the device and the KPPs?
Yes, I can. I'm working on a Wi-Fi system, which is an optical wave-guiding, optical free space communication system. Trying to develop a scanning laser for that. So with a laser, narrow beam laser, a communication link is established between a transmitter and a receiver. So I'm looking for a photonic integrated circuit that generates a narrow beam laser and that can scan through space. So that's the device and the system, and
all the way up. Yeah.
Yeah.
And do you see any differences going from the technology to the device in key performance parameters?
well, I have some difficulties with that. In my system, there's a primary device, which is a photonic integrated circuit, and then there's some secondary, some additional optics.
Yeah.
That maybe you can consider it in that way, that you have a primary laser scanner and then some secondary optics to make it to a complete device.
Yes, and often you see that if you add the secondary things that you add functionality and also get other performance, so that typically results in a number of KPPs that are different.
Yeah.
And the challenge is for people to be aware how things change when you go up in an integration chain. And a challenge that I see often is that people that are deep in the technology are very much focused on, let's say, the prime technical specifications of the technology. And of course, they are essential. That is the differentiating factor of the technology. However, they may not be aware that if you start to integrate it, that, let's say, secondary things may be more important when you are at this higher integration level. So the technology that you develop has to fit in that device and finally in the application. Yeah. Yes, very good. Let's move one step further. So I go back to the presentation, and so we move from the camera now to the optics chain. So if you look, I initially only had the sensor, and the camera mostly adds electronics. And if you go to the optics chain, you see that we add mechanics and a microscope, so more optics. So here you see it in a bigger way. We have an optics stage to move the microscope to the desired position. There is a microscope that can look at the two wafers. There's illumination, making sure that we have light so that we can see something, light sources, and then the information from the microscope is sent into the camera, and then the camera can see both images up and down. And so how is this system used? The microscope looks at a wafer, so then the depth of focus is important, the field of view. I must see the marker that you see at the right hand side, and the marker should be in focus. I need, of course, a optical stage that needs degrees of freedom to move the microscope in X and Y, but it may also have to move in the Z direction. The microscope has its optical properties, the resolution, magnification, and then we had the camera there where we started, and then the whole construct has an alignment of itself. So the camera and the microscope, the tilt of that has an impact on what I'm seeing. So all of these parameters are important at the optics chain level. And then we repeat the same game. So we can ask what are now the key performance parameters of this optics chain, and I already in fact showed them partially in the previous diagram. And you can ask again the same question if you step further out from the device, then to the function, then what are then the key performance parameters? So here you see the key performance parameters that I came up with based on this optics chain example. So let's add these to the spreadsheet, and then you can fill in your key performance parameters. Same problem again. It is so here. So fill in your key performance parameters at the component level. So let's have a look. Dimitris, I see that you have a nice list of things. Can you tell a little bit about your system and the KPPs?
Yes, sure. Can you hear me?
Yes, I hear you. Go ahead.
Okay, so just to brief, we're building a diagnostic system based on our core technology, which is. Would you like me to start a video?
Yeah, just take any start what you want.
Okay. So our core technology is silicon photonic biosensors. We have a photonic integrated circuit hosting biosensors. I had some, it was a little bit challenging of specifying which part is the component, which part is the device, which part is the subsystem. But for the component, given that the technology in the device is mainly our disposable part of the solution, then moving into the component, I've allocated these to optical alignment system, which is basically the system required to align external optical sources and optical detectors, as well as some electrical controls to the photonic integrated circuit. So basically, it's all about the interfaces, and for that, it's important to identify the special resolution, the optical losses that are introduced by the system for coupling light into the chip, the speed that this is done, the mechanical stability of the system, which of course relates to the coupling scheme that we're using, of course the weight and the cost. So that's pretty much some important performance indicators of the optical alignment system.
Yeah. And if I look at your KPPs at the sensor level, and then at the cartridge level, and then at the alignment level, you see a clear evolution of the kind of factors that you are thinking of and about.
Yep.
So you need a different mindset. And another thing that was interesting is, now you did struggle a little bit of what is what level. So what is now a component and what is now the device, and probably later on what is now the subsystem.
Yes.
So I'm throwing many simple questions to you, but answering them can be quite challenging. And you should be aware that the people that in the end may be using your sensor, cartridge, alignment, etc., may all struggle with that. They may not have a clear understanding how the technology is used and built into a device, and then integrated in an alignment system, and how things fit together. And that is what we do in architecting. In architecting, we try to recreate the overview. We try to make sure that we have the storyline and that you can explain to all the stakeholders, to the team, how things work together. Why do we need for this type of system that type of sensor, and why is that an appropriate sensor? So and the two steps there. One step is getting the partitioning right. What is the system? What are the subsystems? What are the components? What are devices? And what are technologies? And there is the question: how do I get the design of the performance right? How does the system work, and how do I get the performance out? And I'm guiding you through this process to show to you how these steps are related. Yes. Erwin, can you tell some about what is your system and your key performance parameters?
Yeah, I started, let me put on the video here. Yeah, so a transmission line, I started on the other side, on the system, subsystem side, to think backwards, saying if you want to have a transmission line, what would be the components that need to go in there, and eventually ending up with the question, what would be the best approach of the technology, the PIC, the VCSEL array, or a copper trace. A little trouble in the middle to kind of sort that out, what exactly should be where, and I end up with cost everywhere. But yeah, that seems to be important at every step.
So
But
let me briefly step into the cost, because that's of course cost is at each level important, but cost is something that has many aspects. So for instance, it can be that in a technology aspect that is important, what could be the cost of the device in the end, or of developing the technology, and those are two completely different kinds of cost. So maybe you can afford to invest a lot of money in order to get a very low cost device. So then the cost of the device is very important, but the initial cost of development may be in first instance less important, because it delivers a very low cost device in the end.
Yeah. Using more advanced equipment, machinery to produce parts, right, in high volume. It's spread out over the high volume and ends up to be more cost effective.
Yeah, exactly. So the trick often is, if you have cost, is try to make cost more specific. Is it material cost, or is development cost, or is it running cost, or so there are many types of cost.
Yeah. In the end, I have it's $1 per gigabit.
Yes. Yeah.
That's everything and included.
Yeah. Yes. So do you have other? I interrupt you at cost. So continue where you were. You were telling that cost often appears. Yes.
Yeah. So and it becomes a little bit challenging. Like maybe I should utilize 3 rows to kind of detail out the different approaches possible, right? Because eventually we want to come to a conclusion which is eventually the lowest cost per gigabit, while still having the right reliability, meeting the right distance and speed. But yeah, there is more ways that lead to Rome, and I think the focus here is on PICs. But is it today better than a VCSEL array, or then just simply a copper trace, right? That's
yeah. And the interesting thing is, what you often see is this: the technology propagates to the higher level, but often at some level the technology becomes invisible, and the options are, let's say, more equal at the highest level. And there may be a cost difference, but in terms of thinking about alternatives, all the detailed things get lost. Yeah, so you may use 3 rows and discover that the right hand rows are quite similar.
Yeah.
Yes, very good.
Okay.
I propose that we take a 5-minute break. So take a bio break, walk around a little bit, and then after the break we'll go further out and see how this evolves. But make sure that you have 5 minutes to get fresh air in your head. So, I hope everyone had enough time for a beer break and a quick outside air consumption. So let me continue. So before the break, we looked at the optics chain, and I'm going to step out once more. So we now will look at the alignment subsystem. And if we look at the alignment subsystem, that alignment has a certain workflow. And the workflow is we have to put the microscope to the marker position. We have to make sure that it is in focus. We search the markers on the wafers. We look for the displacement. We calculate how much we have to move the master. Then we move the master. We again look for the markers and we verify that we are now well aligned, and we may have to repeat this process several times. So in order to understand the alignment, I have to make an alignment workflow, and then I can think about how does this work and how do I use this microscope and the whole optics chain. And if you then look at the alignment algorithm, then it has to look for this marker symbol, and it can look for contrast, it can look for contours. There are many ways that you can build such an algorithm, but you must find a way that you get as accurate as possible at the position of that marker. So now we repeat the same game. So we have the alignment subsystem, and we can make 3 to 5 key performance parameters. And I'm asking you to do that for your subsystem level. And I already did this again for the alignment subsystem. So finding the displacement, that is the important thing. The cycle time, how much time do I need to find the displacement? Being robust for the patterns, the markers, and the condition of the wafers, and then the very mundane aspects of cost, weight, and the size are relevant. So let's go to the spreadsheet here, and I ask you to fill in at subsystem level what you see as the KPPs of your subsystem. Yes, I see that we are getting somewhere. Fedor, can you tell a little bit about your technology and subsystem?
Can you hear me okay?
Yes, I can hear you okay, yes.
Yeah, unfortunately I can't share too much due to the export requirements. I'm in the United States, so there's a little bit of that, but yeah, we do apply this methodology. We do start with, monolithically integrated photonic circuits and turn them into a variety of very useful objects at the end of the day. So yeah, but this is a constructive exercise to actually look at the entire flow of the thing from, wafer to eventual gold box or whatever it might end up being. So yeah, apologies, I have to be this vague, but yeah.
Yes, but your reflection is that you can see how this is challenging, but also useful to get this insight.
Absolutely.
Yeah. So I do this in many classes, and if people work in technology and you go to the right in this spreadsheet, I all the time can feel the pain that participants have. I continuously stretch them out of their comfort zone. So they're very comfortable in the technology, they know everything about it. And you start asking questions, and how is that embedded in the device? And then how is it embedded in something bigger? And the further out you go, the more painful it is for them. And vice versa, if you have people that work on a subsystem and you start to ask them questions about, so what is the sensor and what is the impact of the sensor properties on your alignment, you get similar, let's say, painful discussions. That people say, well, I actually don't know, I'm just using it. Which means that they may not be aware of potential risks and or opportunities. Edwin, can you tell something about what you're filling in? Edwin Hakkanes? You're muted, you have to unmute yourself then.
I thought I did that, but okay. I'm also not going to tell every last detail because of the customer, but we are making a system replacement of an existing system to measure position of marks on wafers. And for this, it's of importance that it's of the same size, that it fits in the same system, and that the performance is equal or better at lower cost. And all the things that are of relevance to your system are more or less also of importance to this system.
Yeah, your example is very close to the example.
Yeah, sorry.
No, very good.
Yeah.
I've seen this more often, so there are more systems working with wafers and alignment.
Yeah. So in the component view, it's important that we can get the right image on the screen and are able to process that image. And in the subsystem, where it's also built into a microscope, also we have to fit it into the system, but we also have to make sure we can do all the calculations needed on the image. Yes. which is left out of the of your presentation right now, and it's also out of mine. But that's a total different ballpark that we're talking about.
Yeah. So one of the main challenges is I use this term key performance parameter, and the challenge is, when is the performance parameter key? So when is it that important that as an architect you should really focus on understanding it? And there are a lot of performance parameters that you can take for granted, and there will be other designers and engineers making sure that it will work. But there are performance parameters which are that important for the functioning of the system at the end, that you must understand how it works and must make sure that it connects to the technology to the left-hand side of this. And if processing is essential, if that is a bottleneck in the way you can cope with it, then probably it will appear in these key performance parameters somewhere. And in my example, we did have quite some processing discussions on how do we detect the markers and how will that impact the accuracy and the time to find them.
Yeah, of course, the speed of operation is of importance.
Yeah.
But on your left hand, in the left columns, you have the sensor, which is, of course, for photonics, the key element to look at. But in my view, it's more a funnel. There are a lot of technologies on the left, which all funnel to a working system.
Yes, absolutely. Yeah, yeah. So it fans out. So if you in architecting, you have to do this much farther. So in the end, you probably have one system, but many subsystems and many components, and in the end are a tremendous amount of technologies. So when I worked at ASML, we had identified, we had a consultancy company going in and making that tree and that graph, and they identified 200 plus really key technologies that were essential to make a good wafer scanner. And so you have to play the game for all the 200 technologies.
Yeah.
Yeah. Yes, very good. Thank you. Let's move up a little bit. Anja, can you tell us something about your system and your technology? Anja Agneter?
Yeah, so for me, it's the
I can hear you, but you have to be a little bit close to the microphone. I think you're very far away.
Is it better now?
Yes, that's somewhat better, yes.
So for me, the most important part is the miniaturization. So everything should be like small and efficient, but as robust and stable as the big system.
Yeah, yeah. And now one of the questions to think about this key performance parameters is, when you are miniaturizing it, where do you sacrifice things, or where does it start to hurt?
Exactly. So we have to weigh size with performance and stability and sensitivity.
Yeah. So sensitivity may go down because you have a much smaller surface, and then Yes, very good. Let's go for the next step in the presentation. So now we zoom out to the printer again. So we have gone all the way from the bottom and we go to the printer. So now at system level, OEM level, you could say, what are there the parameters that play a key role? So again, I have here for the metal printer made the list. And what is it for your system level? What are the key performance parameters at your system level? Yeah, I see many answers arising. Huh? And now to challenge you a little bit further, yeah, so Edwin added customer experience. Huh? Typically, when you come to the system level, you see that more business-like aspects also start to enter into the key performance parameters. So more cost considerations, more things like customer experience. Think beyond only the technology. Start thinking what more is there than let's say the technical performance parameters, but things that your customer will use in deciding to buy from you. So let's have a brief look. Carol, can you talk a little bit about your system and your KPPs?
Okay, I'll do that. Yeah, first, can you hear me?
Yes.
All right. First of all, I'm working for Photon Delta, which is a foundation, and as such doesn't produce anything. We invest in companies that actually will or do are going to do, startups and scale-ups, and we're also trying to help with technical support startups and scale-ups to be successful. Now, I took here as an example what I almost call an imaginary LiDAR system, because as I said, we don't produce them well, but we have a number of companies in our ecosystem that actually deliver bits and pieces on the request of customers, and we found that in a lot of cases they just got a request without having any feeling about what actually was requested and why that was important. So basically what I try to do at some point is to bring those together and then try to work backwards to get to a kind of system specification to see what is important at different levels, because some of the parts are on the component level, some produce PICs, some produce electronics or modules. So we work more or less backward, and that's what you see more here as well. And at the same time, since we help to boost business, we were in Foreign Delta trying to attract outside companies and foreign companies in foreign countries to get interested in our potential. And in order to do that, we had at least an idea about key specifications and the system setup. Otherwise, you couldn't have a good conversation. So what I did was more or less work out the system specification backwards, starting with what customers might find interesting, and then trying to define how that would work out, and then basically asking the customers again whether that fitted their needs, because they were also quite secretive in most cases. So this is a kind of stealth system definition for a totally different purpose than what you normally do. But what it did do was that we were able in the end to define some key parameters of what a LiDAR system could do. There are several versions. You can go back, okay, version could use, in this case, integrated photonics, because that's our area, and what type of requirements you have to meet on module level, because it's clear that we are not going to sell in our system complete LiDAR systems. That's another group. So you sell modules, and that seems to be the value proposition. The modules need components, and in order to do that, you need to get some idea about the component specifications. So that's how you find. But on the very high level, what the LiDAR should do is to give an alarm when it sees something on the road. And for that reason, range, kind of see 300 meters ahead is quite important. Minimum size of what it can detect, and also can it detect that in every almost circumstances. Now, for a camera, dark is different. For LiDAR, bright light is a problem. So those type of requirements you see at that level. Of course, cost is extremely important, because car makers, and I will come back on that in my presentation later this morning, eventually intend to have 4 or 5 of these things in their cars. So price is going to be an extremely important parameter. And for the very same reason, also the size of the system, because you have to build it into a car. And it shouldn't look like those typical cars that everybody has seen on pictures. That's not going to be a selling proposition. So it has to be fitting the aesthetics of a car. Now, then you work back what you then need to do to get done in order to achieve that now.
Yeah.
And of course, over time, there's an evolution in the roadmap. What works today is not good enough in 10 years from now.
Very good, very clear, Carol. So if I listen to you, you see something happening that is also often happening. To the right of the system is, in fact, the super system. So you talked about the car, yeah? And the car has all kinds of limitations and constraints. And the car is driving on a road, so there is a super system, the transportation system, where the car is driving between other cars and other objects. And the reason to have LiDAR is well, you want to detect other objects that you don't want to hit, and whether it's a car or something else. So we have worked now on starting from technology going to the system, but you can go on further and further, and every time that you go further out, you discover more about what is actually needed. And your voiceover that came clearly across. What do you want to do with this thing? Well, the LiDAR, you want to detect things, and therefore the detection is, all detection properties are important, and you want to build it in the car, so the integration properties are important, and the cost. Yeah, thanks very much. Yes. Let me go back to the presentation. So we are now at the system level. If you look at this printer system, you see similar things happening. So I start now talking about print quality. So the quality of the lines on the wafer, and the overlay. So how accurate is this positioned on the wafer? The throughput, how many wafers can I process? Reliability, that is a very crucial thing. It should work in a high volume production environment. So there are many different considerations than we did see on the lower level, although many aspects on the lower level contribute to these higher level key performance parameters. If you have a very poor thermal design, you may end up with reliability problems and overlay and print quality problems. So, in fact, and I already said it when Carol was presenting, you also need to understand the context of the system. So if we look at this metal printer, the process, the way we process these wafers has impact on the way we do the alignment. So it could be that due to the process, we have very little contrast. Or there is a very slow transition, so detecting the boundaries is less well defined. Maybe there are variations in the height of the wafer, so it may be at nanoscale, it may look like a mountain range. There may be shadows from the illumination. The marker may be damaged. So there are many things in the process which is outside of the scope of control of the system builder, but all of them have impact on the alignment function. And if you would go down to the technology, all of them may have impact on the technology we select and the way the technology should be behaving. So little contrast requires maybe a different kind of optical wavelengths or optical wavelengths, etc. So let's briefly go back to the sensor. So we have in the technology a whole design space. We may strive for a higher resolution and a large field of view, and we may want to use red light or blue light. We may have it continuously on, or we may switch it only on when we're using it. And all the time, every design decision that we make has its benefits and it has its disadvantages. So where people in the technology may think that they should do everything to get a high resolution, it may well be that at higher levels that you say, well, I need enough resolution, and if I have too much resolution, I get too many disadvantages. Yeah? If I have a very high resolution image, I use a lot of memory, I may use a lot of energy to process the image, I may use a lot of resources to process it. So high resolution isn't always better. I need enough resolution. Yeah? And that holds for all these parameters. So in this whole chain of reasoning, we have to find out what are the main tensions. What is it that as an architect I should focus on? And that can be at the bottom, you see, it can be they say, well, I need to be accurate enough, it need to be fast enough, and I need to be stable enough. And I have to balance these options. And all the time I can take design decisions where one of the three improves, but another of the three gets worse. So the architecting challenge is to understand this full chain and all the time understand these design trade-offs. And then the challenge is not to compromise, but to find the sweet spot. So to find enough resolution and fast enough. And the sweet spot is there where in the end the system is fit for purpose. What you want to be able to do with the system, you need to be able to do that. So that is everything together. If we now put this into a summary, at the left hand side in the vertical direction you see these different levels. So we see the sensor being part of the camera, being part of the optics change, being part of the alignment subsystem, being part of the printer system. Here we are zooming out. Yeah? And if we look at the sensor, we can also zoom in. There are different concepts. What kind of light do we use? What kind of sensor do we use? And that translates in different designs and different technology choices. So we can also zoom in further from the sensor level. And my message is, in architecting, you have to iterate over these levels. So if you are in the sensor technology, you need to be able to zoom in, really fully understand the technology and design. And you have to be able to zoom out, understand where will my sensor being used and what is importance there. And at each level, an architect tries to find 3 to 5, 7 key performance parameters and tries to understand how they relate to the key performance parameters at the other levels. So that was my summary.